Hey everyone. So this is an example from the notes in section 2.5, which we skipped in class, but I promised you a video. So we're going to be assuming the Bolzano-Weierstrass theorem and using that to prove the nested intervals property. So just as a quick reminder, Bolzano-Weierstrass says that every bounded sequence of real numbers has a convergent subsequence. And the nested intervals property says, if I give you a collection, a sequence of bounded closed intervals, which are nested, so in the sense that I1 contains I2, contains I3, and so on, then their infinite intersection is non-empty. Now, you'll notice I've named my intervals Ln and Rn instead of An, Bn, which we might typically do. And that's really because in the proof I'm about to give, I need to talk about sequences An and Bn. So I don't want to confuse notation. So I'll use L and R for the intervals. Okay, so let's do the proof. So to prove the nested intervals property, we should start from the hypothesis. So we let In be, let's say, an interval Ln to Rn. And for each n, this is a closed and bounded interval. And these are nested intervals. So I1 contains I2 and so on. So that's our hypothesis. And we need to show that if I intersect all of these, it's not empty. So I need to use Bolzano-Weierstrass. Apparently that's the hint. In order to do this, I need to build a sequence. So what sequence do I create? Well, I'm looking at a sequence of intervals. Let's, from those intervals, create a sequence of numbers. So let's, for example, just take A1 to be any random number in I1. You can do this more constructively, but take any number you like. A1 is some number in I1. Maybe A2 is some number from I2, and so on. So in general, just in the I-nth interval, take some random number, call it A sub n. And let's consider the properties of the sequence we've developed. So consider the sequence A sub n. So at this point, it's not a bad idea. Let's draw a picture of what we've sort of discussed so far. So I have my real number line, and I have these intervals. So I have maybe I1 is my first interval. I'm going to try to give different colors here. So I2 might be some other interval like this. I3 might be a third interval, maybe like this. Okay, and that goes on forever and ever. And within each of these intervals, I've picked a random number. So A1 is, I'm going to try to color code it, right? So A1 was a number in I1. Now, I'm not saying it can't, it may or may not be in the other intervals too, right? I'm not saying anything about that. I'm just saying some number from I1. A2 is some number that was in the I2 interval, and so on. Okay. So what do we know about the sequence AN? Well, looking at the picture, something I notice immediately is notice that the A sub n, all of them are actually contained in just I1. And this is because the intervals are nested. And why is this an important observation for all natural numbers? Well, this tells me that the sequence is bounded, right? It has a lower bound, it has an upper bound. So thus, the sequence AN is bounded. The reason this is important to notice is because I can now apply the Bolzano-Weierstrass theorem. So by BW, there exists a subsequence B sub n, which converges, right? Let's call it B, the limit. Okay. So I don't know about you, but my gut instinct tells me that if there's any hope of showing that this interval, the collection of the intersection, right, the intersection is on empty, I sure wonder if that limit B is the thing that's in the intersection. So indeed, let's make that our claim. So our claim is that B is in the intersection of all these INs, which would finish the proof, right? Because then the intersection is not empty. So how do we prove this claim? Well, let's try contradiction, right? When in doubt, contradiction is a nice strategy. So let's assume to the contrary. that limit b is not in the infinite intersection. And all that means is, well, it can't be in all of them, which means there must be some interval in that this b is not contained inside. So that means there exists some n such that b is not in that nth interval. So let's start drawing a picture of this, right? So now I have my interval I sub n. And my assumption is that b, the limit, is not inside this closed interval. Well, notice, by the way, that if b is not in this interval, then I could build a little neighborhood around it, which is completely disjoint from that interval. So let me write that down. So then we can build a neighborhood around b such that, so let me call it this epsilon neighborhood of b, intersect that interval is empty. Now I'm being a little intuitive about this, right? Because I haven't actually told you how to compute this interval or this neighborhood. But, I think if you spend a few minutes thinking about this, like the I sub n we know has bounds L sub n and R sub n. And I bet you can come up with a nifty little formula, even, by cases, what the interval or what the epsilon we would need to be to make these disjoint. Okay, but I think it's a separate problem. I'll let you think about that. Let's focus instead on what we learned from this. Okay, so I have a little epsilon neighborhood around b, which is disjoint from in. Now, of course, at this point, I want to remind us that the intervals in are nested. And so since the intervals are nested, in fact, this epsilon neighborhood around b intersect in is going to be empty, not just for this interval, but for all the intervals that follow, right? And again, let me sort of draw my little picture to sort of convince us, right? In is this interval, I capital N, and now I sub n plus 1 is a subset of that, which certainly is still disjoint from the neighborhood around little b. And if I keep on doing this more and more and more, right, no matter where I am, if I'm anywhere after that capital N, the intervals are going to be disjoint from this neighborhood around b. Well, don't forget, by the way, that by construction, all those little a sub n's, right? All the little a sub n's are chosen from within those I sub n intervals. So I'm going to label them here and here and here. And so I'm starting to see a bit of a problem because all those points in the sequence are going to be outside that neighborhood of b. Okay, so then any b sub n occurring later in the sequence then let me just say a sub capital N. So I'm looking at sort of, there's a point in the sequence, right, where I am now disjoint, right? I'm in this sort of I sub capital N interval. So that's a sub capital N. Any b sub n in my subsequence that are happening after that point are also going to be in that interval, not in the neighborhood. Okay. So any b sub n occurring later in the sequence than a sub n must lie in I sub capital N, and thus those B sub N are not contained in the epsilon neighborhood around B. But now this is extremely problematic because I am saying there are infinitely many, because it's all the Bn that happen after this point in the sequence. So I'm saying, thus, there are infinitely many B sub n not in the epsilon neighborhood of little b. But that means it doesn't converge. So this would mean Bn doesn't converge to B. And of course, that's a contradiction because we know by assumption, or by the Bolzano-Weierstrass theorem from before, that it does converge to B. That's the contradiction we were looking for. So all of this was coming from our contradictory assumption that this little b was not in the infinite intersection, which means it must indeed be there. That completes the proof because now that intersection is not empty and we've proved nested intervals property again. So this is an interesting proof because it's a little different than the proof we did before, but it sort of highlights sort of how we like to think about subsequences, how we think about convergence using this topological definition. So if you have any questions, please come talk to me. All right.